Okay, we're going to continue on. We're on number 26, still in chapter 10 review. And here we're looking at the following problems. Direction. Determine which series converges absolutely or conditionally. If you remember, for conditional convergence, two things must happen. The series itself must converge, and, not if, and the series of the absolute value must diverge. So that's the only way you could have a conditionally convergent series. So, in this case, and we said it's best to start with this first, because if that converges, it's absolutely convergent, and therefore you are done. So if I start with this problem and I look at, first I look at the series of 5 over n, meaning I put an absolute value on the negative. That's really how I got this. Well, this is 5 times the series of 1 over n. If you remember, we agreed if I don't write anything there, that indicates I'm running from 1 to infinity. Anything other than that, I need to write it. So, this is p series, p equal 1, therefore it diverges. Well, this is satisfied. Now I'm going to go ahead and figure out, well, as is. If I look at this series, I notice that 5 over n is positive. It is decreasing. And the limit as n approaches infinity of 5 over n equals 0. Therefore, converge by alternating series test. And the conclusion out of both of those is that, therefore, the original series, since there's only one, you don't need to write it, but is conditionally convergent. And that's the least amount of work you could show. You have to show all of this work. As for number 28, I look at this. There's no way this could be conditionally convergent in the sense, for it to be conditionally convergent, the absolute value must change the nature of the problem. Since this is always positive, either the series converge or diverge, and I could say this is 1 over 2, series n equal 1 to infinity of 1 over n cubed. This is a p series bigger than 1, therefore converge by, well, we said p series, and therefore this is absolutely convergent. So a series that's always positive would either absolutely converge or diverge, and that would be pretty much it. There's not much to do. And I wanted to pick one with a log. The author or the book. On this problem, I could tell right away just by looking at this. Well, this is positive. Right? It is continuous from 2, and it's decreasing. So automatically I could say, well, I'm going to take the integral of 1 over x, natural log of x squared dx. If I let u equal natural log of x, du is 1 over x dx. This would become the integral of 1 over, that is my u squared, and, oops, it didn't register. And that's simply my du. So this is like saying this is u to the negative 2, right? Add 1 to the power, divide by that. That would be negative 1 over u. That's as far as the integral. And that's going to be negative 1 over natural log of n, of x, evaluated from 2 to t, taking the limit as t approaches infinity. Like we said in class, you could do what I just did. This way you don't have to carry the limit with you all the time. Assume it's an integral, and at the end, make sure that you include the limit. And as t approaches infinity, 1 over infinity is 0. Remember, we got that out of section 4.5 that we reviewed. Therefore, converge by integral test. And what do you conclude? It's absolutely convergent, and that would take care of the problem. Next problem on the list is number 34. Well, if I glance at this, now something to keep in mind. When I look at this, again, the way we did this in class, we know the limit of that equals 0. So we already know that this is convergent by the alternating series test. But we should start with the absolute convergence first, because most of the time that's what you end up doing regardless. So if I slap an absolute value on this, that means I'm looking at the series n equal 1 to infinity of 3n squared over n cubed plus 1. There are a couple of ways I could show how this works, right? I know that integral test works for sure, right? I could try the comparison or limit comparison test. The reason I wouldn't really try the integral test, because I have to show this is decreasing. And to show this is decreasing, I need to take a derivative of that, set it equal to 0. But if I look automatically, what dominates the top, what dominates the bottom, that is 1 over n. Remember, 1 over n is a convergence sequence. The series of that diverge. So make sure you put a series. And if I take the limit as n approaches infinity of 3n squared over n cubed plus 1 divided by 1 over n, that would be the limit as n approaches infinity of n cubed plus 1 over 3n squared times n. That would be the limit as n approaches infinity of 3n cubed over n cubed plus 1. I could use L'Hopital once. I could divide by the highest power term of the denominator. In this case, since it's only one step problem, it doesn't really matter. So that is 3 bigger than 0. Therefore, my conclusion is what? They both, what? Which both? This and this, they both diverge by, I don't like that D. They both diverge by the limit comparison test. Well, out of luck. I was hoping this will converge, and I'll say it's absolutely convergent. Now I have to do the other work. Now I have to come in and say, well, look, if I look at that, that is positive. Very good. You could just say that. That is decreasing, not so fast. You have to show me that. You need to take a derivative, so let me just boost this up there. So the alternative, looking at it as is, I could say that red mark is positive. Correct. That is decreasing. I have to show that. I need to take the derivative, and that's going to be, will be what? 6x times x cubed plus 1 minus 3x squared times 3x squared, derivative of the denominator all over the denominator squared. And that would be, if I factor a 3x out of those, I will have a 2x cubed plus 2. And I'll have a minus x left, minus 3x cubed. I will get a 3x into 2 minus x cubed all over x cubed plus 1 squared. And I would look at my, now I'm going to move all of this to the right, just a bit. Here, to leave space for me to do the work here. And I'm going to say, where does the derivative equal 0? Where does the derivative not exist? Well, it doesn't exist when x equals negative 1. We're not going to worry about that because n is always positive. So where does it equal 0? At x equals 0 or x equal the cube root of 2. Well, remember, n is an integer. If this is my derivative and this is f, negative 1 I'm not worried about, 0 I'm not worried about, and I'm looking at cube root of 2. Why should I even bother? Let me start with the next integer bigger than 1, which is 2. If I pick a test point bigger than 2, let's say 3. Well, this is positive. This is positive. And 2 minus 27 is negative. That would be a negative. The function is decreasing. Now you could come here and say decreasing, but you have to specify from 2 to infinity. I could check from 1 to infinity, but what's the point? That's okay. One term is not going to matter. If I let n equal 1 and test the series from 2 to infinity, that's the same thing. And I know already that the limit as n approaches infinity of 3n squared divided by n cubed plus 1, I could divide by the highest power term of the denominator, or use L'Hopital. Since it's only one step of L'Hopital, it makes no difference. Therefore, converge by alternating series test. And what's my conclusion? Therefore, it is conditionally convergent. So if it's conditionally convergent, I really have to do all of this work every time. Not pleasant, but hey, that's what it takes. The next problem on the list. Again, this series cannot be conditionally convergent. It's either absolute or... And I could glance at this and figure out what this is saying. I noticed that, you know what? I could say that's the series n equal 1 to infinity of 2 times 3 over n raised to the n. And if I take the limit as n approaches infinity, that's going to be 0 to the infinity. I could use L'Hopital, or I could say the limit as n approaches infinity of the nth root of the absolute value of 6 over n to the n equals the limit as n approaches infinity of 6 over n, which equals 0 less than 1. Therefore, absolute convergent by the ratio test. And there it is. And on the next problem, I'm glancing at this, and I notice that this limit doesn't equal 0. If I take the limit as n approaches infinity of 1 over e to the negative n plus 1, that is the limit as n approaches infinity. This is 1 over e to the n plus 1. If I clear, that will be 1 over 1, which equal 1, not equal to 0. What does that mean? Therefore, the series diverge by test for divergence. On the next problem, find the radius and interval of convergence. Tell me where is this absolutely and conditionally convergent. This is a quick refresher. This is, I think, text section 10.7. So the way it works, I take the limit, unless this is geometric, which it's not. A sub n plus 1. If you remember, we did that over and over. So let's just write down a few steps on the first problem. That would be the limit as n approaches infinity. This is x to the n times x to the 1 over x to the n. And I combine those, n over n plus 1. That would be the limit as n approaches infinity of x, the square root of 1 over 1 plus 1 over n divided by the highest power term of the denominator. So altogether, I get the limit to be the absolute value of x. And I said to match the book, you just want an x in there. You say less than 1, that's radius. And the interval of convergence, you solve that. That means x is between negative 1 and positive 1. Now, since we didn't use the... Since we didn't, this is not geometric. If it was geometric, I would have been done here because it will be absolutely convergent. But since we use the ratio test, we have to check. Oh man, these colors. I have to check at x, at r equal, or the limit equaling 1. So if I get 1 and negative 1, what happens? If I take n and replace, if I take x and replace x by 1, that will be the series n equal 1 to infinity of 1 over radical n. This is the series n equal 1 to infinity of 1 over n to the 1/2. P equal 1/2 less than 1, therefore diverge. I can't have them. If I take x and replace x by a negative 1, I'll be looking at the series n equal 1 to infinity of negative 1 over radical n. Well, that is positive. We know that. That is decreasing. We could say that because n only appears in the denominator. And if we take the limit as n approaches infinity of 1 over radical n, we get it to be a 0. Therefore, converge by alternating series test. So this is allowed. So we say absolutely convergent for negative 1 to 1, and conditionally convergent only at x equal And that would be my answer. And there's the homework.